Suppose we wish to answer the following question. A stone is dropped from a height of 19.6 meters above the ground, while a second stone is simultaneously projected upwards from the ground with a velocity that allows it to go up to exactly 19.6 meters. So the second stone is able to be thrown upwards so that its top velocity, its peak height is 19.6 meters. It cannot go any higher. When and where do the stones meet? This is the question we want to answer. So to start, let's draw a diagram. So we have some ground, and on that ground there's a building. So there's some building, and this building has a height. And it has a height of 19.6 meters. The ground we're going to call h is equal to 0 meters. And from the top of the building, there's a stone 1. This is stone 1. And this stone initially starts from rest. So you start it here, and then it goes downwards, right? You just drop it. There's a second ball, which starts here at the ground, and you throw it upwards. So this is ball 2, and you throw it upwards with some initial velocity v naught 2. Okay, so v naught 1 is equal to 0 because it starts from rest. And here we'll say that gravity points downwards as usual, and we'll say that the y direction is positive. And since gravity points downwards, that means that our acceleration is negative g. Right? The reason that a is equal to negative g is because y, we've called y the up direction. So, since g is pointing downwards, it has a negative sign in front of it. And I'll choose a different color, maybe purple. And there's some distance, which we'll call s, above the ground. So this distance here we'll call s. And this is the height where ball 1 and ball 2 meet each other. So this is where they pass each other out. Okay, so we want to know when and where this S is. And we want to know when this occurs in time. So to start, we'll begin with ball 1. And I think they call it stone. Yeah, they call it a stone. I'm going to keep on calling it a ball. So ball 1, we have delta D is equal to V naught T plus 1/2 times A times T squared. That's the general equation for us, right? And in particular, we'll consider this equation when the balls reach the height S. So for us, for ball 1, delta D is going to be the final position, which is S. So S minus the initial position, which is H. Here H is 19.6 meters. And this guy is going to be V naught 1, which we've already said is 0. So this whole term is 0, minus 1/2 g t squared. And the reason that it's minus is because A here, the acceleration, is negative g. Okay, then we can multiply both sides by a negative sign, and we get h minus s is equal to 1/2 g t squared. Okay, good. Then we can find a similar equation for ball 2, or stone 2, whatever. Here, we start with the same initial formula, and that's delta D is equal to V naught T plus 1/2 A T squared. Okay, then what's the final position? Well, if the ball's moving upward, then the final position is s, because we're considering the time, or the point, where these balls pass each other. So it's going to be s, the final position, minus its initial position, which is h is equal to 0. So s minus 0 is equal to v naught, which here is not 0, right? V naught 2 is some initial value. Maybe it's like 5 meters per second or something. We haven't calculated it yet, but we can calculate it. So we have v naught 2 times time. And again, this is going to be minus 1/2 gt squared. And again, this is minus 1/2 gt squared because a, as we said before, is negative g. Okay. Now, we can proceed to calculate this v naught 2. To do that, we notice that this ball 2, if I drew its trajectory in this like greenish color, then it goes up, and it goes up to h is equal to 19.6, and then it comes back down. It doesn't go any higher than that. And because of that, we know that its final velocity at a height of 19.6 meters is equal to 0. Right? The reason for that is because if you initially have some non-zero velocity and it peaks at h is equal to 19.6 meters, it has to stop moving up at that point, and then it comes back down. So it goes up, it slows down, it slows down, it slows down because of gravity, and then at h is equal to 19.6, it stops completely, and then it starts to move back down to the ground. And here it only stops for a brief moment, a very, very brief moment, it stops moving upwards. So because of this, we can use the following equation. We can use Vf squared is equal to V naught squared plus 2a delta d. Okay, and we're considering this at the point for the ball 2 going from the ground to its peak. So here, Vf for ball 2 is 0. So this is 0 squared is equal to the V naught 2 squared, which we don't know. We want to find it, minus 2 times g, and that's because a is equal to negative g, times delta d. And delta d here is going to be the final position, which is 19.6, minus the initial position, which is 0. So this is going to be 19.6 minus 0. Then we can write this as 0 is equal to V naught 2 squared minus 2 times g times 19.6. And so we get that V naught 2 is equal to, so we add this guy over to the other side, and then we take a square root. We find that this is the square root of 2 times 9.81, or we'll call it 9.8, times 19.6. And if you plug this into your calculator, you actually get that this is 19.6 meters per second. So great, we found the initial velocity of our ball. Then we can plug this back into this formula here. So let me move all of this down. I'll move this down slightly, and we can rewrite this. We can rewrite this as S is equal to 19.6 times time, because we found the initial velocity to be 19.6 meters per second. So this is going to be S is equal to 19.6 times time minus 1/2 gt squared. Okay. Then, if we add equation 1 to equation 2, what do we get? We can write that down below, but let's just see what we get. We can rewrite these two equations. So if I draw another line here, I want to add equation 1, which is h minus s is equal to 1/2 gt squared, to equation 2, which is s is equal to 19.6 times time. Maybe I'll keep this as v0 2, because we already know what that is. Minus 1/2 gt squared. So, if I take 1 plus 2, then this guy should be equal to, well, if we add these two, we get, on the left-hand side, we get h minus s, right? That's just from 1, plus s is equal to 1/2 gt squared plus v0 2 times time. I'm going to have to move this over a bit. Minus, right? Because this is the second term on the right-hand side of equation 2. Minus 1/2 gt squared. Then we can do some cancellations. So these two s's cancel each other. And then this guy also cancels with this guy. So what we get is that h is equal to v0 2 times time. But we already know v0 2, and we know what h is. H, remember, is 19.6 meters. But we actually found that v0 2 is 19.6 meters per second. So when we solve for time, we get that t is equal to h over v0 2, which when we plug in for the numbers is 19.6 divided by 19.6. So the time at which these guys meet is going to be 1 second. So if I initially drop a ball and it goes downwards, and I have another ball that at the same time I throw upwards, and they meet at some distance s above the ground, the time at which they meet is 1 second after this ball is thrown up and after this ball is dropped. Okay, so now we know when they meet, right? So we got this guy down. We also want to know where the balls meet, which is at a distance s. But what is s, right? That's what we want to find. Well, we can actually plug in for either of these equations here, right? So let's do both just to see that it's actually the case that you can do both. So this will be plugging into equation 1. This will be plugging into equation 2. You can do either, right? I'm going to do both just because I can. So here, equation 1 is h minus s is equal to 1/2 gt squared. Okay. At this position, where they meet, t is equal to 1, right? So h, we know, is 19.6, and then we get minus s, because we don't know what s is yet. And then this is equal to 1/2 times g times 1 squared. Okay, then if you add over s and you subtract over this term, we get that 19.6 minus 1/2 times 9.8 times 1 squared, which is just 1, so I'm gonna leave that term out, is equal to s. And then if you plug this into your calculator, you should get that s is equal to about 14.7 meters. So you can verify that for yourself. And for equation 2, we should get the same thing, assuming we've done everything correctly. So we get that equation 2 tells us that S is equal to V naught 2 times time minus 1/2 times G times T squared. Where here, again, T is equal to 1 second. So 1 second. Then S is equal to V naught T is 19.6. And we multiply that by 1. And then we get minus 1/2 times G times 1 squared. Then we find that S is, 19.6 times 1 is 1, so that's 19.6, minus 1/2 times 9.8 times 1 squared, which is just 1. So I'm going to leave that out here. But if we look back over here, that's the same exact expression we had for S before, right? It's 19.6 minus 1/2 of 9.8, minus 1/2 of 9.8. So we get the same exact answer, which is S is equal to 14.7 meters. So we've solved this problem. And what we have found, just to recap, is that you take a ball, you drop it from a building, which is at a height of 19.6 meters. It's dropped from rest. You then take a ball and you throw it from the ground with an initial velocity that you don't know. But what you do know is that you throw it such that its highest position that it can attain is 19.6 meters. So you can throw it just up to the height of the building, no higher. We then want to find out when and where do the balls meet each other. So they meet at a distance s above the ground, which we calculated to be 14.7 meters. And the time after you initially throw ball 2 and drop ball 1, the time at which they meet is t is equal to 1 second. And with that, I'll end the video. Thank you.